let's get started. Good afternoon. Welcome to our session about streaming. Streamling is a new streaming engine on top of DataFusion. A bit introduction. My name is Xiao Meng. I'm the streaming team lead at Gold Sky.
I'm Rafael. I'm a software engineer at Gold Sky.
A bit introduction of our company. Basically, our company is a data infra company where provide streaming pipeline specialized in blockchain sources. We provide sources from multiple blockchains and offer customers transformations and into their own data sinks. Our customers include Polymarket, Stripe, Circle, and also Phantom. A lot of fintech and also blockchain-related applications. So at its core, what we provide is a declarative streaming pipeline. What does it mean is basically we turn YAML into production streaming pipeline. The user usually provide a topology of their application, which is 3 blocks. One is source, defines the unbounded data of data source, and transform define how it shapes, and then sinks describe where it lands. And the platform basically turns this YAML definition into a production streaming pipeline. In our first generation, we built our platform on top of Flink. Flink is battle-tested streaming platform and is also de facto standard for streaming processing. And it also has this robust fault tolerance mechanism for checkpoint and snapshot management. And for cloud deployment, it has very mature Kubernetes operators for Flink deployment. And we launched our product in 2024 June. That's when the product got GA. And last year, we actually quietly passed like 1,000 pipeline with our product. And over the years, we also come some pain point when implement this platform on top of Flink and a bunch of wish lists. Since like cold start, when you spin up a new Flink pipeline, it may take 2 minutes or longer. And Flink itself has pretty opaque state API. So if you want to manipulate the state, it's relatively hard. The other thing, like we have some customers want BYOC, right? It's relatively hard to do that in Flink because Flink has this distributed job manager, task manager, which is built pre-Kubernetes period. So there's some overlap there, even you have the Kubernetes operator. And a lot of customers is actually application developers. They are large data engineers. They also want transform beyond the SQL. That's another factor. And also, we want to have a relative better local developer experience. You can set Flink locally for sure, but it requires some knowledge. And the last factor is most of our workloads actually stateless. So you don't need that many power features from Flink itself. So we are in this crossroad last year. We have an initial POC called Streamling, which is based on the Rust Arrow DataFusion stack. So we are in this crossroad whether we could continue evolve Flink or we could build a Streamling, a different data engine. And for Flink, there are certain roads to actually improve all of this. But we'll tell a story about we choose the other path to build Streamling. And I will then hand over to Rafael to talk about the data engine.
Yeah, let's talk about the engine internals. We're going to go through how we built it, why we did it, and what people exactly need in a streaming engine that Flink doesn't have and that we might provide to customers. Our Flink era started a couple years ago. We, until this day, have thousands of Flink pipelines running our infrastructure. They are there for real customers that rely on it. We benefited from Flink's big community for its mature ecosystem, battle-tested code. And we really love Flink. Like, we still run it. We still need it for many things. But somewhere along the line, we started to feel the pain points. Flink is a complex tool. It has lots of features. It allows you to do exactly one's processing and a bunch of other things that are kind of cool, but our customers didn't really care about. And the other thing is it has a real dollar per month cost. So like if we're running thousands of these pipelines, then thinking about that and trying to optimize for lowering the cost really makes a lot of sense. Looking at what our customers actually ran as workloads, they tended to be CDC for out workloads where they would read from one database and spread that data to multiple databases for analytics, maybe fire some webhooks for specific events and things like that. They would maybe do some enrichment and transformation, maybe some deduplication, but they didn't really do any joins in Flink like we thought they would when we started building the first version of our platform. They didn't really do aggregations or windowing or any of the things that are really cool in Flink. And we at some point just realized that we don't need distributed shuffles or we don't need keyed state to run all these workloads. We are paying for a complexity that we could not cache in, and therefore like we're making our customers pay for more than what they needed. So at some point we started trying to design a tool that would serve our customers better. Around 2022, 2024, we started noticing that DataFusion and Arrow were kind of becoming really mature. They were already being used for building query engines for batch processing, but around somewhere in that time frame, people started noticing that it could be used for streaming as well, and they started merging PRs to make that possible. And we thought we would benefit from that. So we kind of started a POC to get Streamling going. And this is not one of our goals from the beginning, but this is kind of how our platform is known today by our customers. This is the now. Like, we had this problem with Flink taking too long to start up, taking 2 minutes or more for certain pipelines because of all the overhead, all the chit-chat between job manager, task manager, and so on. And our customers didn't like the waiting, like it was too much for the developer experience that they wanted to have. They wanted something more snappier where they could iterate in their SQL queries faster. And what we ended up achieving, even though it was not our main goal, was it takes about 5 seconds from pause to start from a pipeline to actually start running. And this is like an average across all our pipelines that we have in Streamling. So it's a really significant number compared to the 2 minutes that we had before. And how did we actually do that? So like we're not claiming to have built a better Flink just because we use Rust or Arrow or DataFusion. That's not what we did. We actually scoped a project that's much smaller and kind of anchored down to the things that we actually care about, to the things that our customers actually need. A few of them are filter expressions, projections, UDFs, operations like union all, unnest, subqueries, CTEs, and things that do not require distributed shuffle, do not require keyed state. And if you look on the other side, we have like all these cool features that Flink has and that are useful to many, many people out there. To maybe 1% of our customers still rely on things like that. But streaming joins, streaming aggregations, windowing, exactly once delivery. Our customers seem to have found other ways to doing that. Many of them just do that in their own databases. after they sync to ClickHouse, they can do their analytics and can do things closer to the database where they feel more comfortable and don't have to touch that on the Flink side. And by scoping that out, we actually built something that's much more focused, doesn't have as many complexities as Flink. We built it on top of DataFusion. If you're not familiar with DataFusion, DataFusion is essentially a collection of Rust components that you can use to build query engines. We try not to fight it. We extend it where it needed for specific things. So DataFusion has a SQL parser, a logical planner, a physical planner, optimizer rules, and vectorized execution, and other things that you are certainly going to need if you're going to build a query engine. And we try to use as many of those operators as stock as possible. We do not modify them, except in a few key places. So like the places where we actually touch DataFusion to make it slightly different for streaming are table providers, which are essentially how we declare sources and sinks. We can say we have a Kafka source as a table, and that's how DataFusion knows that it can read data from the table and kind of pipe it through the stream. We have some changes to execution plan to kind of declare our own operators, like things for interacting with HTTP servers, things for allowing a pipeline to share data from a source without having to read it multiple times, and kind of share the data through other operators of the stream broadcast to them. And a bunch of other operators for like JavaScript transforms and whatnot. We have some other changes to the extension planner and physical optimizer rules that allow us to change the behavior of some stock DataFusion operators very slightly so that we can pass in checkpoint markers. And that's about it. The whole trick that makes this possible, that makes DataFusion kind of work as a streaming engine as opposed to a batch engine, is essentially that we can tell DataFusion that our operator has unbounded boundedness and emits results incrementally. So you can tell DataFusion that something is expected to run forever, and you do that by declaring an execution plan with that type of boundedness and incremental emission. You can tell it that it does not require infinite memory to compute the results. And in your implementation, I have an example here as what we have for a Kafka source. In your implementation, you just return a stream that yields record batches forever. A record batch just being a collection of rows with a schema and some metadata. That's kind of like the default DataFusion data structure that gets passed around for all the operators. And to DataFusion, the plan of a batch pipeline and the streaming pipeline doesn't differ very much. Because of the choices that we made, the pipelines look pretty much the same. So you can have on the left a batch pipeline that reads Parquet files from a file system, object storage, or something like that. It applies some filtering. It does some projection for some columns and writes that data back to a Parquet sink on the same file system or somewhere else. And on the right side, you could have a streaming pipeline basically doing the same thing, but just reading data from Kafka, which is an unbounded source that we declared like the one I showed before. And we can use the exact same filter operator, projection, and maybe write that data to a file sync like before, or maybe write it to Kafka just to keep things more real time. And the point here is we can keep every operator that DataFusion has as stock as possible. We don't have to change it. And the streaminess actually lives at the source. That's where we define our Kafka source, our ClickHouse source, and other components that actually are unbounded. One other thing that we needed to make to kind of turn DataFusion into a streaming engine was figure out the story around checkpoints. So our customers do care a lot about at least one semantics. They need to know that whatever progress the pipeline has made up to a certain point is going to be captured and it's not going to roll back once a failure happens. So we introduced checkpoints to guarantee at least one semantics. And the way it works is very simple compared to other engines. Because Streamling is not distributed, a lot of the complexities that come with checkpointing just go away. And the protocol that I have here on screen is essentially we have a coordinator that sends a marker for epoch n to all the sources in the pipeline. The marker rides through every operator on the stream, and it rides in the form of a schema metadata in the record batch itself that allows us to keep data fusion operators as they are without having to modify them. That the checkpoint information kind of rides implicit to the whole stream. And once that reaches the sink, and the sink actually has the opportunity to flush data downstream and guarantee that the data is durable, the sink can actually acknowledge that epoch back to the coordinator. And once the coordinator receives all the X for all the sinks, it sends the finalizers to all the sources, which then are allowed to commit their offsets, because at that point, data is already durable downstream. So it's like a simple checkpoint mechanism. We do not have a state on intermediary operators. So this is just like for source state. One other thing that we did that's kind of unique to Streamling is we allow people to transform data with more than just SQL. SQL is the de facto choice for many of our customers, but many of them do not like it or need slightly different ways of transforming data for particular operations. So on the left here, we have one option being like the sandbox WebAssembly transform. You can write either JavaScript or TypeScript, and you get this process function, basically data in, data out, that you can use to transform data, and you can stick that inline into the YAML that I showed before. And very easy to manipulate JSON with that, manipulate text, and some other things that might not be as neat in SQL. Also, very low barrier to entry, so people tend to like that. It does have some performance costs compared to everything else, but it's definitely a choice that people make sometimes. WebAssembly does not have access to the file system or network calls or any other things, kind of like sandboxed. And it runs alongside the pipeline in a JavaScript runtime. The option in the middle we call external HTTP handlers, which is essentially a protocol for the pipeline to communicate with an external service that lives on the customer's infrastructure. So the customer can host a web service that responds to API requests in JSON. It responds to post requests. And people use that to enrich data sometimes. It's very easy to do it. You can do it in whatever language you use because it's outside of our infrastructure. You manage however you want it. You scale however you want it. We will allow customers to send concurrent batches, and you can scale up your service based on that. People will also use that for getting CDC data with an envelope about whether it's an insert, delete, and then they can process that on their end however they want. We do guarantee at least one semantics by using retries with backoff and retrying infinitely. And some of our customers use that for avoiding to share like code that's sensitive to them and publish that to our infrastructure. So if some code is sensitive, they hide that behind their infrastructure. They just exchange data with the pipeline, and then we don't see any code that's sensitive to them. Sometimes they also like to make a bunch of API calls on their end with their tokens and their own infrastructure rules and everything, and then just communicate data back to the pipeline. That obviously has like the network cost between wherever they host the service and our service and everything. We encourage people to run things on the same data center or same regions if at all possible. But it's a different pattern, very flexible, and our customers like it a lot. The last one is native plugins. This is the most performant out of all of them. We essentially allow users, partners to write plugins for source transforms in pretty much every operator that we created in DataFusion. And you can write that as a Rust crate. You publish as a dilib, and that gets loaded during the pipeline startup. There's zero copy of data buffers between the plugin channels and the pipeline, so it's very efficient. There's some metadata that gets copied, but it's very negligible. And everything is auto-managed by the pipeline runtime. You don't have to worry about checkpoints or any other thing. You just basically data in, data out like the other ones. But you can opt to participate or to configure some of those things more closely if you have the need for it. The other thing is because everything is a plugin, we don't have to merge that code into the core engine. Like anybody can write that as a separate lib in a separate repo. And it's very easy to one-shot new connectors with that today. Like we have internal teams that just in the past week have published like an event bridge connector for AWS pretty quickly. And like you can get something, I would say like in 5 minutes running, publishing data, and then you can customize it however you want for the specific features that you care about with a little bit more prompting. But it's a very easy to just add connectors that we don't have. Right now we have like native connectors for Kafka, ClickHouse, Postgres, and a few other things that were there from the beginning. But if you do need a new connector that we don't have, it's very easy for you to add one. So the last thing that I want to talk about is what we have in terms of observability. We do have open telemetry metrics for every node in the pipeline. So you get metrics for tracking progress of offsets at the source, for tracking epoch progress for checkpoints, throughput, latency, everything. But something that we do that's unique to us and that you probably won't see out there in other engines is we have a terminal UI that you can use to inspect data live in every pipeline node, but syncs. So like you can see what data is traveling through the source right now. You can see what a transform's outputting. And that's very helpful for debugging. Like whenever your pipeline gets stuck and you don't know exactly what's going on, you can go there and inspect what's doing, as opposed to having to add some logging, restart the pipeline, redeploy, and wait like 10 minutes for it to happen. Everything, it's kind of wrapped in a way that has a fixed cost, so it doesn't cost you much. We enable it by default. You can disable it if you want it, but has very minimal cost. As a recap, I talked about a specific point in time where we are in this design space. Like we're not trying to rewrite Flink in Rust. That's not what this is. We're just trying to craft an engine that's really good at the problems that we actually have and have that cost being as low as possible. I talked about Arrow and DataFusion as the substrate for building this engine. And I talked about checkpoints and how they provide at least one semantics and source progress tracking. Also talked about 3 extension paths that we have beyond SQL, WebAssembly for sandbox transforms, HTTP for service calls between the pipeline and an external service, and native plugins for first-class performance. The last one, observability by default. We do believe that debugging is very important, and we try to make that as easy as possible. We have metrics for every operator, and we allow live inspect from any source or any transform. Now I'm going to pass it back to Xiao for the second part.
Okay, so we have this data processing runtime. Now, the next stuff we want to figure out is how to build a product on top of that. So this is mostly about how to turn the YAML into a production-ready streaming pipeline. And that's how we built our product, Turbo, end of last year. So at the very top, you will see what you want to figure out is probably just turn into from a pipeline definition into Kubernetes deployment. But underneath, since we want to support multi-tenant pipeline, we need to figure out tendency isolation, also metrics, building security, also risk management of the pipeline. Risk management of data processing runtime, and then reliability and support. We won't talk all of this today, but I will just give you a rough idea about what the control plane looks like. So from the left or right, the user interact with web interface, web UI, we have a visual pipeline builder to do that. And we have the CI to actually access that from the command line interface. And of course, you have agent to actually gauge the CI access and build the pipeline for you. And we'll have a bunch of skills available, so the user can actually use the skill to build the pipeline. And all those go through a public API server. And the goal of public API server is just serve the user request. And that will be forwarded to our control plane agent, which is basically the control plane in charge of orchestrate the Kubernetes deployment and access other state. So from the control plane, it will spin up the pipeline for each project. And the project itself, each pipeline will send out open telemetry. So we have a separate telemetry pipeline, which serves two purposes. One is some metric is useful for billing purpose because we have this usage-based billing. So we ingest a certain metric into ClickHouse for billing. And the other type of metric is exports to user as well. So we provide Grafana-based dashboard to users. And they can also customize with alert system. And at the bottom, we'll talk about how we manage state for the checkpoint. So we'll talk about this a little bit later. And go back a little bit back from the API server to control plane agent, we actually also log all those events to an audit table in ClickHouse as well. So every request will be recorded in ClickHouse. This allows us build a lot of feature on top of that. And of course, for secret management, we actually have a secret provider which available from the API server. So user can create a secret from the API server, and also this secret will be available. And the control plane agent can access this API to read this secret, and those secrets can be then used for Kubernetes deployment and Kubernetes secret map to manage that. So, okay. So now I will focus on this part, how the control plane actually spin up the Kubernetes deployment for the pipeline. So at a very high level, we are talking about two components. The tenant in our platform, we use project as a unit of tenant, right? And the pipeline contains two parts. One is topology, which is the source transform things. I talked about earlier, that's a YAML definition of what data want to be processed. And then the other part is runtime metadata, the lab, and whether you want this as a job model instead of continuous stream. And resource size is basically how much resource you want to assign that. Or we also have a special config override where you can override a lot of deep internal behavior of the engine. So all those, the tenant and the pipeline go through the streaming cloud, basically the control plane. And to make it simple, we make a very simple naming convention of the pipeline. So all those Kubernetes object is follow this naming convention. So it will be project ID and then dash pipeline. So it's very small naming convention, but it's very useful in internal operations. So you can identify which project is and which pipeline is. Of course, we use a lot of Kubernetes label to allocate a lot of internal state or internal attribute of the pipeline. So with that, what the user sees is actually a simplified version of Kubernetes CLI. They will see high-level command like you want to apply the pipeline, you want to pause, you want to resume or delete. And this is more like a state machine of various state of the Kubernetes deployment. I won't go into too much details here, but basically, we have abstraction of this state, and let user only see this full command to operate the pipeline. Okay, so that's the control plane to data plane part. Now I want to go back to the API server to control plane agent part. So the API audit table is actually basically an event log of all the requests. You have things like project ID, name, operation, request, response. Hash is the config hash. Version difference, status code, headers, and created at. Two important attributes here is request payload, which is basically the pipeline definition. And then the headers, you can associate a lot of metadata with headers. So something like who created the, who performed the operation, and what's the source of operation, whether it's an AI agent, whether it's your visual editor, whether it's a CLI, or whether it's by us for any internal operations. So with that, you can build a operation history of the change of the pipeline, and also like difference for the pipeline change, which is very useful when you try to customer support debugging and try to figure out what's wrong, whether this is some issue from the user side or this is some issue from the platform side. Okay, so that's about the audit table part. Next, I want to talk about the StateDB part. So we use Postgres to actually store the state. What the state looks like is basically 4 components. You have the namespace, and then you have the key and data. So it's more like a key value store. And then you have the timestamp show when this key was created. For example, in this case, the namespace here is the deployment name. So the first part is the project, as I mentioned earlier, and the second part is the pipeline name. So you can use that as namespace. And the key here is, for this particular part, you can simplify that as a Kafka topic and then partition. So this is basically says what the consumer offset for this particular topic to that 42 partition. And data itself is a JSON object. So when you design your own source, you can put any data structure there. So for Kafka, we only store the offset and then update it at timestamp. And this is very useful when you try to debugging any checkpoint-related issue, right? If you are familiar with Flink, when you try to access a checkpoint and try to figure out what the checkpoint data looks like, it's very hard. And for this one, you can just use SQL query on the state database. So we have some use case when we found a certain bug of the checkpoint, and it's very handy to first use SQL query to analyze what the blast radius of that issue. So you can easily write any SQL query based on, let's say, a certain type of project or on a certain type of Kafka topic have this certain issue. And also, sometimes, let's say you found the issue, and for whatever reason, the pipeline travel back in time because the state is broken, or for whatever reason, you can also write some script to update the state with SQL. So that's another benefit of this. Okay, to recap, we keep it simple for the cloud deployment using naming convention instead of, and leverage Kubernetes as much as possible. And we also record wide requests, so you can use that to derive new features. And also, we have this StateDB make operation much simpler. And with that, I also want to mention all the contributors for the project. We have on the upper lot of contributors contribute to the data processing runtime, and we have other contributors. As Rafael mentioned, the plugin system makes it very easy to contribute, even you are not a streaming expert. Okay, then we also have some news announced today. We also open source this today. And here's the QR code for the repo. And the license is a functional source license. Yeah, if you're interested in the start the repo, clone it and play. And feel free to contribute and raise any issues there. Yeah. With that, any questions? We also prepare some demo if we have time. Yeah.
Thank you very much. So we do have time for 1 or 2 or 3 questions. Are there any? Yes. Give me a second. I'll bring the microphone to you.
Thank you so much. Thank you so much for the presentation. It was a really nice talk. My question is around the control plane and then like all these diagram. Is it like a BYOC kind of setup? Like a control plane is managed by you in your own setup, and then the data plane is the cloud of the users? Like how this is distinguished?
So, we do offer the BYOC option. So the control plane, right now the control plane and data plane is at the same Kubernetes cluster. And the control plane is written in Rust as well, so Kubernetes Rust. And you can install this control plane agent, what we call, and in your Kubernetes cluster, right? And then the agent will be responsible for spinning up the data plane and the data pipeline there. So we do offer a BYOC option for that.
Okay. And my question is how, when you offer that option, for example, you own the control plane and then we own as a user the data plane part, how it's being charged? I mean, it's charged based on some like CPU usage or?
We haven't figured out that yet. So it may be charged by enterprise offer. Yeah.
All right. Are there any more questions? You? Yes.
Thanks for the talk. Yeah. So for the open source solution, what is the minimum infrastructure you would need, like Kubernetes, ClickHouse, and Postgres?
So open source, I believe we support Kafka source, and there are things like ClickHouse, Postgres, webhook. There are a bunch of others as well, yeah. For the runtime, we do have a demo. If you check the README, we do have a local setup where you can set up your K3s cluster and then spin up a sample pipeline there. So if you go to the getting started guide of the GitHub, you will see there's a getting started, which help you set up a local Kubernetes cluster and set up Kafka, and then some data in Kafka topic, and then you read from Kafka and write to, I believe, Postgres. Yeah.
All right. Thank you very much. Give it up again for our speakers, please.